Hello. In this video, we're going to cover the topic of the kernel of a group homomorphism. Let's begin by recalling that a homomorphism between groups G star and G prime star prime is a map phi from G into G prime such that phi of x star y equals phi of x star prime phi of y for all xy in G. Now here is our definition of the kernel of a homomorphism. So the kernel of a homomorphism phi from G into G prime, where G star and G prime star prime are groups, is the set of all elements x in G such that phi evaluated at x is the identity of G prime. This kernel is denoted by ker parenthesis phi parenthesis, but it is pronounced kernel of phi. Let's do an example. Let A be the 2 by 3 matrix whose first row is 1, 2, 3, and second row is 4, 5, 6. And let phi be the map from R3 into R2 be defined by phi of x equals AX. We're going to show that phi is a homomorphism between the groups R3 plus and R2 plus. And we're going to obtain the kernel of that homomorphism. Now here is our goal. If I want to show that phi is a homomorphism between the two groups R3 plus and R2 plus, what I want to show is that phi of x plus phi of y equals phi of x plus phi of y for all xy in R3. Now observe that phi of x plus y is simply, by definition, A times x plus y. Here we have that this is the product, the matrix multiplication of the matrix A and the matrix x plus y. Recall that the matrix multiplication distributes over matrix addition. So AX plus Y is the same as AX plus AY. But by definition, AX is phi of x and AY is phi of y. So we end up with phi of x plus phi of y, and this is for all xy in R3. So our goal is complete. Phi is a homomorphism between the two groups. Now on to the computation of the kernel of phi. By definition, the kernel of phi is all elements x in R3 such that phi evaluated at x is the 0 element of R2, the identity element of R2, which in this case under addition is theta. So what we want to do is solve phi of x equals theta. But remember, phi of x is defined as AX. So we aim to solve the equation AX equals theta. Now we know A is the matrix 1, 2, 3, 4, 5, 6. X is an element of R3. So we're going to write it as x1, x2, x3 equals 0, 0. Theta in R2. Observe that this is simply a system of two equations in the variables x1, x2, x3. The two equations are 1x1 plus 2x2 plus 3x3 equals 0, and 4x1 plus 5x2 plus 6x3 equals 0. What we want to do is we want to solve that system We want to find all vectors x1, x2, x3 that will satisfy the system of equations. Now here we are going to use a little bit of linear algebra. When we have a system, we can write it in matrix form as an augmented matrix. In this case, the augmented matrix is 1, 2, 3, 0, 4, 5, 6, 0. In order to solve this system, what we need to do is we need to convert this augmented matrix into a reduced row echelon form matrix. For that, recall we have to apply elementary row operations. So let's begin by figuring out how to get rid of this 4 here. The elementary row operation that does that is row 2 minus 4 row 1. Row 2 minus 4 row 1. So let's do the calculation. 4 minus 4 times 1 is 0. 5 minus 4 times 2 is 5 minus 8. 5 minus 8 is negative 3. 6 minus 4 times 3 is 6 minus 12. 6 minus 12 is negative 6. 0 minus 4 times 0 is 0. Observe that in the present matrix, we could reduce the second row if we divide it by negative 3. The elementary row operation that does that is row 2 divided by negative 3. So 0 divided by negative 3 is 0. Negative 3 divided by negative 3 is 1. Negative 6 divided by negative 3 is 2. 0 divided by negative 3 is 0. Now, our next step, get rid of these 2 up here. What elementary row operation will do that? Well, take row 2 minus 2, take row 1 minus 2 row 2. Row 1 minus 2 row 2. So let's do that. 1 minus 2 times 0 is 1. 2 minus 2 times 1 is 0. 3 minus 2 times 2 is 3 minus 4, which is negative 1. 0 minus 2 times 0 is still 0. At this point, we have achieved our goal. We wanted our matrix to be reduced into a reduced row echelon form matrix. Now I write the system that this augmented matrix represents. x1 minus x3 equals 0. And x2 plus 2x3 equals 0. Notice that here we can solve for x1 in terms of x3, x2 in terms of x3. So this results in x1 equaling x3 and x2 equaling negative 2x3. So then our solution to the system is all x1, x2, x3, all vectors x1, x2, x3, where x1 equals x3, x2 equals negative 2x3, and x3 is itself. Observe that you can move out the parameter x3, the constant x3, and end up with all multiples of the vector 1, negative 2, 1. So in conclusion, solutions are x1, x2, x3 equals to 1, negative 2, 1 times the constant x3, where x3 is a real number. Consequently, the kernel of phi is the set of all vectors in R3 of the form 1, -2, 1 times x3, where x3 is a real number. Now, let's write an exercise here for the audience. The exercise is the following. Let A be the matrix, the 3 by 3 matrix, 1, 2, 3, first row, 4, 5, 6, second row, 7, 8, 9, third row. And let phi from R3 to R3 be defined by phi of x equals ax for all x in R3. Your goal is to show that phi is a homomorphism between the groups R3 plus and itself, and then to obtain the kernel of phi. Once done with this exercise, carrying out similar details to the ones shown in our example, you have understood this example. That's all for now.